very special guest with us. His name is Ehteshamul Karim. He's a PhD candidate at the University of Pittsburgh. His talk today is titled Measuring the Immeasurable, A Hunt for Neutrino Mass, where he will present his recent work on behalf of the Project 8 experiment. So, Bhaiya, the floor is yours. So you can go from here.
Okay, thank you. So today I'll talk about this endeavor in the scientific community about measuring the neutrino mass. This has been an effort from experimental particle physics folks for at least the last 20 years or so. So yeah, I'll just give a brief overview of the journey up until now and what we're doing as an experiment to progress this further. So let's first talk about a very classic problem that arose in particle physics in the 1930s and 40s. So you have a tritium atom, which undergoes a beta decay to give off an electron. Now, the nuclear reaction that occurs in this case is you have a neutron in the tritium that decays into a proton and an electron. Now, if this was just a two-body problem, then what you would see is um, this energy distribution like this blue line here. So what this means is that since the neutron is supposedly static, so after decay, the energy momentum would be distributed among these two particles. And when that does, since proton has a very definitive rest mass and is much heavier than electron, thus the electron would have a very certain energy, which is at around 18.6 keV. Now, when we try to measure the energy spectrum of the electron, we see that that's not the case. Rather we see this red curve. So that means that there must be some new physics. Now, Wolfgang Pauli hypothesized that there must be a third particle, so it must be a three-body interaction instead of a two-body interaction, where the third particle, neutrino, carries away some of the energy momentum from this decay process. So what happens by adding this new particle is that you have energy momentum conservation, and the total angular momentum, that is the spin of the two sides of this equation, is also conserved, and the lepton number is also conserved. So let's talk about this particle, neutrinos. Neutrinos are present everywhere, and by everywhere, I mean it is the second most abundant particle in the entire universe, coming second only to the photon, so light particles. So this shows some sources of neutrinos at different energy scales. So you can see that at very low energies, you have neutrinos coming from Big Bang, which are called relic neutrinos. You also have neutrinos coming from inside the Earth. You have neutrinos from sun, from reactors, from atmosphere, so cosmic ray collision with atmosphere, from supernovas, from particle accelerators, even from galaxies, and from unknown sources, extragalactic sources. And they have different cross sections, so different measurement probabilities. Now, where do neutrinos stand in the standard model? You have the standard model with quarks and leptons, and then the force carriers, the bosons. So neutrinos lie in the lepton section of the standard model. And this is just a diagram to demonstrate how neutrinos react with the rest of the standard model. So as you can see, neutrinos only interact with the rest of the fundamental particles through weak bosons. So they're not very interactive, not as much as other particles, so electrons or other quarks. Now, one interesting phenomenon that we discovered a while ago is that neutrinos oscillate in flavor as they travel distance. Now, what we mean by flavor is that these flavors are superpositions, quantum superpositions of distinct mass eigenstates. Now, just to break this down, you have different mass eigenstates of neutrinos, and what they do is they oscillate in their contribution to the flavor state as they travel distance. So when we interact with a neutrino, we only see the flavor side of things, but when they propagate through distinct mass eigenstates. Now, this oscillation probability between flavors depend on the mass square difference. So for a two-flavor model, the probability can be given by this expression here. So you can see that the delta m square must be non-zero if the probability is non-zero, assuming that the mixing angle is non-zero too, which is the case. So this is a plot that shows how the flavor fraction between the different flavors change as a function of distance. So you can see that the flavors oscillate with distance. So this means that since we are observing the oscillation of neutrino flavors, then the delta m square is not equal to zero, and so neutrinos have non-zero mass. So this was observed by two experiments, SNOW experiment, Sudbury Neutrino Observatory, and Super Kamiokande experiment separately. And so they received a Nobel Prize in 2015 in physics. Now, oscillation measurement gives us the squared mass difference between different mass eigenstates. So these are called delta m12 square, delta m13 square, delta m23 square. So although they tell us that, they cannot tell us where the absolute zero lies. So they tell us the difference between mass states, but they don't give us the origin of the mass yardstick. Now, there are a couple of methods that people have tried to measure neutrino mass with. One is observing or estimating neutrino mass from cosmology, particularly from large-scale structure. The other is by observing rare decays, such as zero nu BB, which is neutrinoless double beta decay, which I'll talk a bit about. And then the classic method, which Pauli actually proposed, which was beta decay spectroscopy. So measuring the energy spectrum of the electron that is emitted from the beta decay. So the last two are obviously laboratory based. Now, just to briefly mention how we can measure neutrino mass from cosmology. In the early hot universe, assuming that neutrinos were massive, they would pass through matter clumps because there's a lack of interaction, and the neutrinos had much higher energies back then, so higher thermal velocities. So what they do is they suppress the small-scale structure growth, and they enable large-scale structure instead. So this is just showing two different scenarios, a simulation with neutrino mass assumed to be zero, and the other where neutrino mass is assumed to be 1.9 eV. And you can see that with different neutrino mass, you have different large-scale structure in the universe. So by observing the large-scale structure of the universe, we can place upper limit on the neutrino mass itself. So the dark energy spectroscopic instrument experiment, the DAISY experiment, used the CMB measurement to provide the upper limit of neutrino mass. And what they found by assuming that neutrino mass is greater than zero in their model is they found the neutrino mass to be smaller than 72 millielectron volt. They sometimes have negative neutrino mass, which is unphysical, according to our known physics. But that's one of the issues, that this model, this measurement has model dependence. It uses a lot of priori assumptions and uses lambda CTM and other extensions to the model. So one thing is cosmological experiments place upper limits, as I just mentioned, and oscillation experiments effectively place lower limits as to how low the mass can be. Now, one question that arises is, why are neutrino masses so low? Because as you can see, these are the different fundamental particles charted according to their mass values. And you can see the next lightest particle to neutrinos, which is electron, has about 10 to the power minus 3 gigaelectron volt mass, whereas even the heaviest known neutrino have around 10 to the power minus 10. So there are orders of magnitude differences in mass. Now, there are a lot of theories that speculate how they may have gained such low mass. One is, if they're direct neutrinos, there could be seesaw mechanism that comes into play. And if that's the case, if neutrinos are direct neutrinos, then it would be connected to matter-antimatter asymmetry of our universe through a process called leptogenesis. So whatever the case is, if we can measure neutrino mass, that would mean that standard model would need updating in order to account for the new physics for neutrino mass generation. Now, I talked briefly in the past about two different methods for neutrino mass measurement. One was the endpoint method, that is the beta decay spectroscopy method, where you have the tritium atom, which then decays into helium and emits an electron and an electron antineutrino. There are some rare decays, such as neutrinoless double beta decay, where you have a large nuclei, which then decays into another large nuclei with 2 extra protons and 2 electrons. And what happens is the neutrinos, the antineutrinos that emit from these 2 beta decays, they cancel each other out because we are assuming that the neutrinos are the antiparticle of itself. So they can annihilate. But sorry, this requires Majorana, nature of neutrinos. So I'll focus mostly on the tritium beta decay because this requires a certain nature of neutrinos, which we don't observe yet. So let's just stick with the most grounded physics version of our measurement that we're trying to make. Now, as I mentioned earlier, the electron energy distribution looks something like this for tritium. Now, if we zoom in on the spectrum near the endpoint region, you can see that for different neutrino mass, the spectral shape changes. So if you have no neutrino mass, then you would have this black curve here. But if you increase the neutrino mass, the spectral distortion increases and the endpoint shifts to the left. So we can essentially measure the neutrino mass by observing the spectral shape very closely. Now, I'll talk about the current status of tritium beta decay neutrino mass measurement. The Catrin collaboration has the world-leading direct neutrino mass limit, and it is 0.45 eV, that is 450 MeV, using roughly 2/3 of a year of data. So this plot here shows the theoretical limit based on the oscillation experiment measurements of the neutrino mass for 2 different scenarios, one for the normal ordering, one for the inverted ordering. Now, all this means is the ordering of the mass eigenstate values. So they expect to go down to 300 millielectron volt after their full data set, which is a 1,000-day data set that they just finished. So that is nowhere near the inverted ordering region. So we at least want to go below that in order to exclude that neutrino is either within this region, neutrino mass, or it is not inverted ordering, but rather below. So it must be normal ordering. So Catrin has some limitation for which they can go below 300 millielectron volt. Their energy resolution roughly scales with volume. Now, they already have a volume of 10 meter for their spectrometer, and as you can see, it's quite a mess trying to move that in. So significant scaling of the spectrometer to improve sensitivity by orders of magnitude is not realistic for their case. And the other thing is they're using molecular tritium for the decay and not atomic tritium because of its challenges. So that has a fundamental limitation at 200 millielectron volt. So they really can't go below that. And 200 millielectron volt is still way above the inverted ordering limit. So we need new technique and atomic tritium to further improve the sensitivity beyond the inverted ordering limit. This is where this novel technique comes into play, cyclotron radiation emission spectroscopy. This originated from the brilliant minds of two of our collaborators, Joe Formaggio from MIT and Ben Mondriel from Case Western Reserve University back in 2009. So the idea is you have the atomic tritium or tritium in general, which decays into helium-3 and emits an electron. What we do is we trap this electron or we guide this electron through a magnetic field so that it undergoes cyclotron motion and emits cyclotron radiation. Now, in order to measure the frequency of this radiation, we trap this electron long enough. And to do that, we use a magnetic bottle trap. Now, cyclotron frequency depends on the electron kinetic energy, and there's a one-to-one correspondence between them. So if you can measure the cyclotron frequency well, then you can measure the kinetic energy. That is, you can construct electron spectrums with enough of these electrons. Now, I'll mention how the electron moves in our trap. So it is trapped in a magnetic field with higher pinch values closer to the trap end, so closer to the trap coils. What that means is that the magnetic field magnitude is higher near the trap coil ends. Now, there are three kinds of motion, as you can see here. There's this cyclotron motion, which is demonstrated by this red curve. And then there's the axial motion, so the back and forth motion of the electron as it's going through the trapped region. And then there's also a grad B motion. So why that happens is, so this grad B motion is this displacement of electron azimuthally, as you can see here. And that happens because the magnetic field value changes at different Z values. Now, one thing that happens as the electron is moving back and forth is since it experiences different instantaneous B fields, that's why you have a local change in the frequency, which causes frequency modulation, as you can see here. So there are sidebands to our signal. Now, this is what a CRESS event looks like from our data acquisition channel. So you have an incoming time series data from our waveguide or cavity, whichever we're using to measure, and it is dominated by noise, obviously. So what we do is we do a short-time Fourier transform, and we stack the Fourier transform results in time. So each of these bins, or if we take a slice, the y-axis Now, what happens in this case is the electron starts at a given frequency given by this So what happens is the frequency, the energy starts going down, which means the frequency starts going up, as you can see here. And then after a certain point, the electron that is emitted scatters with some other tritium molecule or atom in the trapped region. And as it scatters, it loses more of its electron. It essentially has an energy loss jump. So that causes a frequency jump upwards. So you have this energy loss causing the frequency jump. Now, to reconstruct the kinetic energy from the CRESS events, we need two things: the start frequency for that electron and the magnetic field it experiences. Now, this is a picture of the field lines for different radius and different axial position. And as you can see, the magnetic field that an electron experiences depends on where it starts in the trapped region and also on the momentum. So if the electron starts at a more slanted direction, it will so we need to precisely reconstruct the start frequency, and also to understand what magnetic field it experiences, we need to reconstruct the position, the starting position, and the initial momentum of the electron, which is, in our case, expressed by this angle, pitch angle, alpha. And we need to do this for like each single electron to do this magnetic field correction. Now, how magnetic field affects our signal is that if an electron is closer to, let's say, 90 degrees, so almost perpendicular to the magnetic field, then it will move less in our trap on average compared to an electron with smaller pitch angle, so with more slanted direction. So what happens in the close to 90-degree case is that you have electron with a certain carrier frequency, carrier band, and then side bands, axial distance apart. But as you lower the pitch angle, what happens is the average magnetic field that it experiences increases because it's moving back and forth more to a higher axial extent. So the average magnetic field that the electron experiences is more, which causes a shift in the carrier band of the signal. And the other thing that happens is that since the modulation increases of the signal, the sideband separation also increases. So one thing to note is sidebands come primarily from axial motion in the trap. So we need to really reconstruct pitch angle and also position, but pitch angle primarily to precisely reconstruct this electron energies. So this is our experiment. There's a lot of folks working on many different aspects of solving this hard problem. And why this problem is hard is because this electron signals that you see have an energy of like 1 femtowatt for at least the current data taking scenario. So reconstructing signals at 1 femtowatt is really hard. Now we're adopting a phased approach. So we started with phase 1, where we used waveguide to detect this electron signals. And that was to demonstrate the first electron spectroscopy with CRESS. For phase 2, we also used waveguide, as you can see here. Now, this was the first demonstration of continuous spectrum measured with CRESS with an EV scale resolution. And we also provided our first effective neutrino mass upper limit, which was less than 152 electron volt. And we were just using a 1 millimeter cube cavity, which is like super small compared to the 10-meter that Catherine uses. So for phase 3, we are changing our readout technique. We're going from cavity to waveguide to cavity. And we are planning to use large volume CRESS. There's 2 steps to phase 2, which is starting small, so just testing whether we can measure this using cavity. And we're using cavity crest apparatus for that. And it is starting data taking in a week from now. And this has an energy resolution goal of 0.3 eV, so sub-electron volt energy resolution. And then we are also planning to scale up to multi-meter cube volume in what's called the low frequency or low field apparatus, LFA, which I'll also talk about. And then we are also doing atomic source development because, as it turns out, getting atomic tritium is one of the hardest problem in nuclear and particle physics, and that's why Katrin avoided it. But we have made a lot of progress and we are seeing light to actually use atomic tritium in our experiment. And then there's a phase 4, which we'll have, where we would make the neutrino mass measurement if the neutrino mass lies above the inverted ordering region, because this is our goal, which is going below the inverted ordering region. So saying that this is our goal, there's just showing this graphically. So we set our limit of energy resolution at around 1.7 eV in phase 2 with a neutrino mass upper limit of 152 eV. Now we are here, we are doing CCA measurement to decrease energy resolution by an order of magnitude. Then we plan to increase our volume, so scale up the experiment, and also get the first results with atomic tritium, and then decrease the energy resolution even more and scale up to phase 4, which would give us the final, which would help us reach the final mass sensitivity of 40 MeV. Now, there's a couple of requirements to reach this sensitivity. One is you need to understand how effective volume affects neutrino mass sensitivity, the runtime, the source gas density, the background, and also the energy resolution and its uncertainties. So this is a model that we came up with after understanding the systematics of our experiment. And this is where we lie in terms of phase 3 values. And this is where we are supposed to go in phase 4. And the y-axis shows or the twin y-axis shows the 90% confidence level in our neutrino mass value. Now, what we can do to increase this sensitivity is we could either boost up our source gas density to a level that helps us achieve our sensitivity to lower levels, or we could boost up effective volume, we could mitigate background, and then also we could mitigate our energy resolution. So I'll go by one by one each of them and show what we're doing. So in terms of effective volume, we are working to we're hoping to trap electrons better, and what that would do is it would increase the efficiency of the detection. So we're working on magnetic trapping. There's a lot of components to magnetic trapping. So we need background magnet to do the cyclotron motion, and then the crest trap to trap the electrons so that it doesn't go outside the detector volume. We need Yoffie trap for guiding the molecular or atomic tritiums, which I'll talk about next. And there are like subsystems like external field shielding. So field shielding from Earth. So Earth's magnetic field causes distortion in our experiment. So we are working on that. We are also getting correction systems. So jitters in the coil currents causes jitters in the magnetic field. So we are developing a feedback system which would correct that magnetic field jitter. And we're also doing magnetometry, so trying to measure the field values and not through just simulations. So these are some efforts at different institutes. So this is at UW, University of Washington, where they're using NMR spectroscopy to measure the magnetic field inside the cavity volume. And this is some coil characterization that's being done at Yale University for the coil winding that is going into our current trapping. What else we can do is we could also increase the effective volume by getting the cavity to that we've started making designs of building for LFA. And as you can see, it's a huge cavity with about 4 meters of height. So there's a lot of interesting measurements that we're doing with prototype cavities. So how the mode would change. So essentially getting a mode map through beat prototype cavity. So what that enables is that it helps us understand how the signal would be picked up at different regions of the cavity volume. We're also considering doing multimodes. So this one that you see here is for TE011 mode, the transverse electric 011 mode component. Now, what that does is it picks up the carrier band really well, but it doesn't pick up the sidebands as much because of the resonance, because of the sidebands being away from the resonance of the cavity. Now, you could choose a different mode, TE012, which picks up the sidebands much more than the carrier bands. Now, for this, there's a lot of work going on in developing multi-mode cavities. And this is something that shows how the distortion of the cavity would affect the eigenmode structure for the different modes. So a lot of cavity R&D going on. Now for source gas density, I'll just mention why we are using this gas, why atomic tritium. I briefly mentioned it earlier, but where the challenge comes from is we get tritium in our nature as molecule and not as atom. And when the tritium molecule decays, it makes a tritium helium molecule, as you can see here, which has vibrationally excited states. So as an electron tries to go out of this molecule, the excitation absorbs a random amount of energy, this molecular, this vibrational excitation state, which smears the endpoint, as you can see here. So the electron endpoint is now smeared for the tritium, for the molecular tritium case. For atomic tritium, this is not the case. So this smearing limits the sensitivity of neutrino mass. That is how precisely we can measure the spectral shape to about 200 millielectron volt. So we are doing some advances in tritium science, and this is a paper that came out very recently where we came up with a scheme to cool down atomic tritium after the atom cracker essentially cracks the molecular tritium to atomic tritium. The technique is called MECB, so magnetic evaporative cooling beamline. And all it does is you change the confining field through the Yoffe trap that I mentioned before, and I'll be showing it next. And as you drop the confining field, the hot atoms that are generated through this atom cracking, they evaporate. So you only have the cool atoms that goes in. So this is the Yoffe trap that I was mentioning. So you have currents flowing in through the different metal cables at different directions, and that essentially creates a hexagonal trap inside. So through this Yoffe trap and through other considerations, so dipole losses in tritium, we see that we can calculate the loss rate as a function of temperature. And since we're operating at cryo temperatures, so that noise thermal noise doesn't become an issue. So we can see that at very low temperatures, the loss rate varies in this form, in the like the black curve here. So in order to keep the source gas density constant or to tune it to our preferred level, we needed to understand how the tritium is lost in our detector volume. And so we understand that now, which is a great advancement. Now, there's one other thing that we could do to reach this sensitivity. That is by reducing the energy resolution of our experiment and also the uncertainty on the energy resolution. So I'll talk about how we reconstruct this electron. So we have the incoming data blocks, and then we perform a trigger. So just picking up this portion of the signal, the portion of the data acquisition that may have this crest event signals. And once we do that, we have the portions of the signal that may have crest events, and then we try to do a parameter estimation. So we try to reconstruct the pitch angle and the position of and the starting frequency of the signal through different reconstruction algorithms. And then we try to, and then we put some cut. So we try to say that, okay, let's take all the electrons within pitch angle 88 to 90, because that may have signals that is more preferred to our analysis. And if that's the case, then we store them. And there are different techniques for this reconstruction, this parameter estimation part. So there's matched filtering, there's log likelihood, so that's maximum likelihood estimation. And we're also using machine learning techniques, and I'll go through each of them briefly. And we're doing this both on time and frequency domain. So as a first line of attack, we're using a sideband-aware sequential track finder. Now, what that does is we have our spectrogram. What we do is we put a power cut. So we throw off all the values below a certain power. And so we have this kind of a sparse spectrogram with fewer points. Now, the portions of the signal would have higher power compared to the noise, because that's how we've configured our detector. What we can do is we can do a clustering and track classification on this sparse spectrogram. And we can also get the sidebands of each of these tracks. This is the recent development that's been done in phase 3 and wasn't present in phase 2. And we need sideband-aware reconstruction for event by event B-field correction, because as I mentioned, we need pitch angle, and pitch angle affects sidebands. So now we have developed an algorithm that can detect carrier and sideband simultaneously. So the red curve here shows the sideband and its power, the carrier band and its power, so zeroth order sideband. And then the second order sidebands are also visible. The first orders are missing due to Doppler shift not being present, but we can talk about this in question answer session if you like. So this will be implemented as a first line of attack with CCA data for reconstruction. Then there's another algorithm that we are looking at, maximum likelihood, and also match filtering. So this gives the best possible reconstruction for our current setup, and it provides a point of comparison for other algorithms. This just shows how we're doing the reconstruction. So you have an incoming time signal, this black curve here. And what you do is you slide that in time through a signal template that is a simulation where you know the parameters exactly. And then you try to do a correlation between these two at different time delays. And once you do that, you can see that the portion of the incoming data which has signal will have higher correlation. And that and then you can place a cut, let's say 0.5 correlation, and say that, okay, this portion of the signal, this portion of the incoming data has signal in it. So then we can also say that the signal must have a parameter similar to those of the signal template if there's a best match between different signal templates. What else you can do is you can reconstruct by doing a chi-square fit of the incoming data to the to simulations at different parameters. And by doing that chi-square fit and then putting a confidence interval, you can also get the energy resolution out and also reconstruct the energy of the electron. So this is what it looks like, where we are doing a maximum likelihood estimation, different energies and radius of simulations, and comparing that with the incoming data through the chi-square fit, and then putting 1 sigma, 2 sigma, and 3 sigma bounds. Now, since these require a lot of simulations and each simulation takes a lot of time, it is computationally prohibitive for reconstructing events directly from data. So we're looking at ways to reduce simulation runtime or combining machine learning algorithms such as better optimizers to fit better, and also coming up with analytic model, which I'll talk about next. If we do that, then we could use a lot of machine learning algorithms. With data, we could also define an analytic model instead of doing this simulations that would generate the signals. So this is one such analytic model developed where we say that the electron has a given amplitude and then its frequency changes. And then there's some other parameters such as the initial phase of the electron and then alpha, which is the cyclotron radiation loss factor. So based on this model, we can do a fit of the data. So this is a fit of the data when there's no noise. And as you can see, the data agrees really well with the model for a 90-degree electron. Now, this plot on the right shows how well it can reconstruct when there's noise in the data. So the blue curve is the noisy input data, and the orange curve is the noiseless data that is hidden inside this noisy data. So we can see that we can also fit very well to the underlying noiseless signal with this model, at least for a 90-degree electron. So this model is currently on par with maximum likelihood estimation or mass filtering algorithm when we guess the parameters pretty good. So what we're doing now is optimizing fitter so that out and developing analytic models for all events. We're also using machine learning algorithms. In phase 2, we used a UNet approach. Now, what that meant was there was a two-step deep learning scheme. So what we did was we first took the spectrogram and we scanned for each pixel and attributed a probability of that pixel being in a track. And then we also used a lightweight classifier to just classify whether portions of the spectrogram had tracks or not. So we've almost optimized this approach for CC reconstruction, which will also be used at a later stage, hopefully. We're also exploring graph neural network, which initially shows good division of noise and signal bins in the spectrogram. And we are also doing state space or using state space model for time series reconstruction. This has its own perks, such as more interpretability because there's physics involved, and the memory also scales linearly, and it provides decent energy resolution, about 0.5 eV without noise. So that's pretty close to our target. With noise, things change a bit, but we are trying to measure noise in order to fit that into the model training so that we can get rid of noise too. Now, what all of this means for Project 8. We are planning to have better position and pitch angle reconstruction, which will mean better energy resolution since we'll be correcting the magnetic fields better. So what this will do is it'll demonstrate an order of magnitude improvement in phase 3, which will then ensure scalability to larger volume. And this will hopefully lead to phase 4, where we'll measure a neutrino mass. And this is also kind of a successor of Catrin. So we're hoping that it works out good. Thank you. I will take any questions, and please visit project8.org if you are interested in the experiment. And you can also reach out to me if you want to know more about neutrinos. Thank you.